Alright, in this video we are going to talk about diodes. You may have seen this circuit diagram symbol somewhere. So we have an arrow with a line like that. And this arrow is to indicate that current can only flow in one direction with a diode. So we're going to think of a diode like a one-way valve for electrical current, with the caveat that we mean positive current. We have a video much earlier in this series defining conventional current as the flow of positive current. So in reality, in a metal conductor where electrons are the charge carriers, electrons are actually going the other way. But this is just kind of the convention used in physics and electrical engineering for positive current. So that's the direction the arrow is pointing. We have a positive side of the diode called the anode, and the negative side called the cathode. So, as we will talk about in more detail in this video, when the diode is forward biased, or the voltage on the anode or positive side is above a certain threshold relative to the cathode or negative side, then it's going to conduct. And when it's not, when that voltage difference is too low, it's not going to conduct. So the diode is made, since I just said it can conduct sometimes and not other times, we say it is made from semiconductor materials, which are somewhere in between conductors like metals, which pretty much always conduct, and insulators, things like wood, plastic, rubber, which pretty much never conduct. Semiconductors are in between. Sometimes they can conduct and sometimes they don't. And you can go watch entire videos about the physics of this. We are just going to kind of gloss over it at a really, really high level in this video. So when talking about diodes, or if you go read a textbook chapter introducing diodes, you'll hear about something called a PN junction, where a diode is made from a junction of two different types of silicon that is doped or has additives of different types that give it different properties. So the P-type silicon is doped with boron, and that gives it extra holes, or mobile positive charge carriers. If you think of the absence of an electron as the presence of a positive charge, there are extra holes in the P-type that can move around. And then the N-type is silicon doped with phosphorus, which gives it extra mobile electrons. So not an extra, that doesn't mean the N-type has a net negative charge, because there's still an extra proton in the nucleus of the phosphorus atoms to cancel that out. So there's not a net charge, but there are extra mobile electrons that aren't bound to a specific atom, so can move around easily. And again, you can go watch entire videos explaining the physics of this far better than I will here, but the net effect there is that current can only flow in one direction due to a whole bunch of stuff about electron orbitals and valence bands and energies and all that physics stuff we're not going to get into here. As far as we're concerned, we just care that the combination of these two materials creates a junction where positive current can only flow in one direction, and again, the actual electron flow, if that's what you care about, is in the other direction. If we look at the IV curve for a diode, just like we've done for other components like resistors, we are going to see something like this. Now, this isn't drawn perfectly to scale, but, sorry, I forgot to label my x-axis here as voltage, my y-axis is current. And for positive voltages, so a positive forward voltage across the diode, we're going to have almost no current until we reach a threshold voltage at which the current is going to increase very, very rapidly. And for a silicon diode, that threshold voltage is usually somewhere in the 0.6 to 0.7 volt range. If we reverse bias the diode, so apply a backwards voltage across it, then we're going to get pretty much no current. We might have a very small leakage current in kind of the nanoamp range, or even smaller than that, until we get down to a voltage that is negative enough, so tens or hundreds of volts depending on the diode, where the whole thing breaks down and then reverse current is allowed through. So there's your breakdown voltage. And then this forward voltage, you might see different things depending on which textbook or video you reference. So forward voltage drop, you might see that abbreviated just as a subscript V with a subscript F, or in some textbooks V with a subscript gamma. We kind of, so sorry, I should back up to say that this behavior is nonlinear, right? Compared to, say I mentioned a resistor where we have Ohm's law, V equals IR, that's a linear relationship. You're going to get a straight line on a V equals IR graph. We clearly have a nonlinear relationship here with different regions. Usually for purposes of this course, we're just kind of focused on the positive upper right quadrant of the graph. We're not too worried about leakage current or breakdown. And again, I didn't draw this perfectly to scale, but this part where the current increases is steep enough that we effectively model this as just two constant regions. One where we just have zero current, so at any voltage less than the threshold voltage, including a reverse bias or negative voltage, we just have zero current, and then we treat it as a constant voltage drop or constant forward voltage once you reach that threshold, but you can't have a higher voltage drop than that. No matter how much you try to increase the voltage, the diode is just going to keep conducting more current, but it's going to be at a constant voltage drop, and we'll go over some examples of what that means a little later in this video. But first, I think I'm going to try and cram this all in one slide here, and then we'll go over to a new slide. I think a mechanical analogy that is very helpful here, again, if you're a mechanical engineer, this series is really made for people who are not electrical engineers, is just to think of a one-way check valve with water. So here's my little sketch of a flap that can open in a pipe. And if I have water flowing through, if there's enough pressure on this side to push open that flap, then water is going to flow through that way. But if I try to push water through the other way, if I reverse the pressure, then the flap is just going to close, and there's this little stopper here that's blocking it. So current cannot flow through in the other direction. Again, you always have to be careful with water analogies when discussing electronics because you can take them a little too literally. So this is not literally what's going on with electrons or mobile holes. There isn't a little flap or gate in there physically stopping them from moving, and the physics of what's going on are more complicated. But again, I think this analogy helps. Just if you're using the fluid analogy, think of it like a check valve that lets current through in one direction, assuming you have enough pressure to open the flap. So if there's not enough pressure, again, we kind of have this minimum threshold voltage. It doesn't start conducting right away at 0 volts. So if I just have a little itty bit of pressure, it's not really enough to open the flap, then I'm still going to have 0 current flowing through. So you have some minimum pressure to open the flap. Once you have enough pressure, you open it. And then eventually, I'm kind of running out of space to draw this, you kind of open it all the way, and you can't really open it more. Okay, so that's kind of representing this constant region of the graph where, again, you're not going to get more pressure because you've kind of maxed out. You can't go above that pressure or voltage. Again, not perfect, but intuitively, I think that kind of helps if you don't really understand all the physics going on. Again, just think of it like a check valve. Lets current flow through in one direction, but not the other direction. So let's look at a couple simple example circuits here, and then we'll probably break out some subsequent topics into a few separate videos about diodes. So say I have a battery connected in series with a resistor and a diode, and that diode has a forward voltage drop of 0.7 volts. I have a resistor of 1 kilo ohm, and say the battery or voltage source is only a half volt, so 0.5 volts. The question is, what is the voltage here, if I call that V out in the circuit? And I'll do this as a multiple choice kind of concept question so you can think about it for a second. Is that voltage A, 0 volts, B, 0.5 volts, C, 0.7 volts, or D, 1.2 volts? So if you want, you can go ahead and pause the video here, think about that conceptually, or do the math if you have to. What is V out in this configuration? Voltage source of a half volt, a 1 kilo ohm resistor in series with a diode which has a forward voltage drop of 0.7 volts. Okay, coming back, hopefully you paused the video. The correct answer in this case is going to be 0.5 volts. And you might ask, well, wait a minute, you said the diode has a forward voltage drop of 0.7 volts. Why isn't it 0.7? And remember our IV curve, IV, we don't have any current flowing through the diode until we reach 0.7 volts, our threshold voltage. So this is 0.7. If we are below that, we have no current flowing. We can effectively treat the diode like an open circuit. And as we've seen in some videos earlier in this playlist, if we have an open circuit, if we have no current flowing through this resistor, so the current through the diode is 0, it's in series with the resistor, therefore the current through the resistor must be 0, then we know the voltage here is 0.5 volts. There's no current through the resistor, then due to Ohm's law, if current is 0, the voltage drop across this resistor must also be 0. So then V out is also going to be 0.5 volts. So before we've reached that threshold voltage and the diode is conducting, again, no current flowing in the circuit, output voltage is just equal to the source voltage. Now let's ask what happens, okay, if this voltage goes up to, say, 1 volt. I have the same circuit. I have my diode, I have my 1 kilo ohm resistor. I'm just going to erase here, okay, and ask the same question. The diode still has the same physical property of the forward voltage drop is 0.7 volts. What is V out in this circuit? Again, go ahead and pause the video, think about it, and I will keep talking in a second for the answer. Okay, so in this case, we are going to have 0.7 volts. This voltage that I am applying is above my threshold voltage, so the diode is forward biased, but note that that does not mean I have 1 volt over the diode itself, okay? I can't really exist out here in this region of the graph. For this simplified model, the drop over the diode has to be 0.7 volts. Again, for a real diode, that line isn't perfectly straight, it's just very, very steep. And so in reality, you can keep getting higher voltage, but your current is going to get so big that you're going to blow up the diode. So we are using the simplified model where we treat that voltage as constant. So we have a 0.7 volt drop across the diode, which means V out here has to be 0.7 volts. But we now have, we know the voltage here has to be 1 volt, so we have a small voltage drop across the resistor. We're going to have 1 volt minus 0.7 volts is the voltage drop across the resistor. And if we want to, we can then use Ohm's law to solve for the current through the resistor, where again I is equal to the voltage drop, so that's 1 volt minus 0.7 volts divided by our 1 kilo ohm. And being careful with units, that's going to be 0.0003 amps or 0.3 milliamps. So, something interesting you will note here is this output voltage does not change if I keep increasing this voltage. Just say if I increase that to 3 volts, I am still going to have that forward voltage drop 0.7 volts across my diode, but I am going to have a bigger voltage drop across the resistor and therefore more current through the resistor now. So I'm going to be dissipating more and more power in the resistor, but I am clamping or limiting the output voltage because it's just always going to be this drop across the diode. So that is why you can hear this circuit referred to as a voltage clipper. So if this is time, if I vary my input voltage and say 0.7 volts, the forward voltage drop of the diode is right there. So sorry, I should have labeled that. That is my input or source voltage. My output voltage is never going to exceed the value of the voltage drop across the diode. So it will follow along if the input voltage is below that, but it clips the input voltage when it exceeds that value. So there are many, many different applications of diodes and other circuits you can build that make use of this functionality. This is just one very simple example. We are going to be covering a few more in some subsequent videos in this playlist. But again, since this is just kind of a high-level introductory view of diodes, we're not going to go through the tons and tons and tons of useful diode circuits This is just one example. If you want to see those, I recommend picking up a textbook or going and checking Wikipedia or something. You can find a much bigger list. In the next video, we are going to talk about light-emitting diodes, which you see all over the place around you as these little indicator lights on electronic appliances. So here is the symbol for a light-emitting diode, or LED, and we are going to give them their own video.